feel a bit out of place after the three presentations. So hopefully not as bad as it seems. So this was a joint collaborative work with IIT Bombay and Tufts University. One of the collaborators is here, Samir. So just briefly introduce the motivation. It's not a traditional motivation in the sense of an IoT or a sensor network, but the focus is mostly on the sensor node itself and can we make it reconfigurable. That's the first outset, and then a brief discussion on the reconfigurable sensor node itself, and where does this analog compressed sensing falls into picture, and then the proposed design and some results and so on and so forth. So again, I would like to stress that the motivation here is a remote sensing node, wherein accessing or the accessibility is a challenge. So you have multi-sensor node where you have a power-aware hardware, a very simple instrumentation hardware. But what we would like to do is no change in hardware, but can you reconfigure the node with a simple software fix? So that's the problem statement that we are trying to solve. So reconfigurability without physical access to the node itself. And possible application scenario is, okay, let's say you have a node which is remotely installed, and then you have some sort of debugging or a servicing or an application change which requires the resolution of the node to be changed by itself. But I don't have physical access to the node itself. So that's the setting at the outset. So traditionally, if you look at a traditional chain where you start from the sensor all the way up to the receiver, so you have a signal conditioning, and then you have, let's say, a 4-channel MUX, and then you have an ADC, and then the data is then serialized and then transmitted, right? So now the challenge is you have a signal conditioning circuit, so you have an ADC, which means that it needs an anti-aliasing filter. So you have a fixed bandwidth. And then you have something called as an amplification, just so that you can map the sensor output to the ADC full scale. So this mapping basically sets the gain of the chain, right? So I need to be reusing the entire full scale of the ADC. So the challenge now that we have is, if I want to reconfigure the resolution, the first solution that I have is I replace the ADC straightforward as is. But then again, it means that I need to have physical access to the hardware, which is again not possible in this scenario. The second possible solution is I go for the highest possible ADC. Let's say I put a 24-bit ADC and my application requires 8-bit, right? So I only operate it in that 8-bit range. But the problem in this case is that the gain of the signal conditioning now has to increase, because I need to now map to a new signal range. So you have a dependency of either a hardware change in the ADC side or on the signal conditioning side. So on the traditional signal chain, this seems to be a problem. So what we're trying to say is, without any hardware fix, is there a software fix? So the proposed hardware is something like this. So what you do is you do away with your traditional signal amplification. What you do is you make a simple hardware such as a relaxation oscillator, where your sensor itself is a part of the oscillator, and the frequency of the oscillation maps then to the sensor value. So that's the first change that we have. So now what you get is possibly a square wave output whose frequency is mapped to the physical parameter that you're trying to measure, right? So, and then because the output is digital, now you can shift all the way directly to the digital domain. So then you have a case-to-1 digital MUX to multiplex between multiple sensors. And then what you do is this is where the crux of the things change. You do a 1-bit quantization rather than an n-bit quantization. So you take the oscillator output, you do a 1-bit quantization, and the quantization is happening at Nyquist rate with respect to the oscillator output. Okay, so that's one more change. So what we do is basically the signal conditioning is replaced with a simple relaxation oscillator, and then you do a 1-bit quantization with respect to Nyquist of the oscillator itself. Okay, so those are two changes. And then what you're trying to do is the resolution reconfigurability itself is how many bits do you transmit to the receiver. So now based on the number of bits that you sent, you try to reconfigure the resolution of the sensor node itself. So what we're trying to say is the complexity of the entire thing is pushed to the receiver's end. So the transmitter is pretty loosely put, very hardware aware, because you simply have a relaxation oscillator, a MUX of D flip-flop, and then basically a transmitter. Okay, so the entire problem statement now is, can you estimate the frequency of your transmitter with this quantized 1-bit quantized data at the receiver side? Okay, so yeah, so how to precisely estimate the frequency with these m bits that you have sampled at the receiver. So this is where compressed sensing comes into picture. Of course, compressed sensing itself is a 1-hour lecture, so I'll probably briefly highlight a few important things. So compressed sensing itself relies on sparsity, meaning to say that if I take a sinusoid, the signal is sparse in the Fourier domain because I have only one component. So the information is basically very sparse in the Fourier domain rather than the time domain, right? So I can use that sparsity and I can define something called the dictionary of atom. In the case of DFT, the atom is basically the number of frequency components that you have, right? And then you have a sparse matrix, which is basically sampling the sparse dictionary of atoms. So what compressed sensing tells you is how many measurements do you have to make in the time domain to now reconstruct the signal in the actual to reconstruct the signal without much error in the set of sparse dictionary that we already have. Okay, so this is a basic version of compressed sensing. And then what you do is now the problem statement is boils down to a convex optimization problem. You're trying to estimate the frequency of operation using these m bits. Okay, and then a convex optimization problem is similar to L1 norm minimization. So a special case of this is something called as line spectral estimation. And the problem with traditional line spectral estimation using compressed sensing is that because you have a dictionary of atoms, these dictionaries are discrete in nature, right? So what if the frequency that I want is not on the dictionary of atoms, if it is lying somewhere in between, right? That's the problem, because then you cannot represent your input as a signal in a signal with sparsity in any domain, because you are neither here nor there. Okay, and this is where you have multiple solutions. For example, one solution is you increase the number of grids itself, right? You make the grids finer and finer and finer. But the problem is as you go finer and finer, you have numerical instability in the algorithm itself. That means that you have a reconstruction error. Okay, and so with that problem, we come to analog compressive sensing, where in 2018 there's a landmark paper from UC San Diego, where what they did was they proposed a method called as superfast line spectral estimation. Now, unlike the traditional compressed sensing, what you do is you don't estimate a frequency value. You estimate something like a probability distribution function of the frequencies itself. So you have now access to all possible analog values of frequencies, unlike a discrete frequency value. So if you now can solve this problem at the receiver side, which is basically trying to solve the line spectral estimation with PDF estimation of the frequencies, then you basically have access to the actual frequency itself. Okay, so this is something not new. We had proposed earlier a very high resolution MEMS readout, because now a MEMS can be excited with a single tone. And let's say you're using this MEMS for some particle measurement, and based on the particle weight, the resonant frequency shifts, let's say by 0.1 hertz, 0.2 hertz, right? So what we had shown earlier is that you can measure precision as high as less than 0.5 parts per million. So if you have 1 megahertz, you can actually detect 0.5 hertz frequencies using these techniques. So this work we're proposing now is slightly an extended version of what was proposed earlier, wherein what we're saying is, okay, let's say you have this n number of nodes, and each of these nodes basically is simply a relaxation oscillator, a D flip-flop, and the transmitter. What we do is based on the resolution requirement of your application, you change the m bits of data that you want to send. Let's say if m is 16, 64, you get different resolution at the receiver side. Okay, the only thing is you have a small node, and then you send m bits to the receiver, and the receiver takes care of everything else. Okay, so a simple prototype basically looks like that. For example, you have a relaxation oscillator. In this instance, you have 4 nodes. Okay, these are simple relaxation oscillators, and then we have made the design modular so that you can extend this to higher number of nodes. And then you have a simple Marx D flip-flop implemented as a centralized unit. Okay, and then you have a BLE, which is a part of this ESP32. Now, if you look at this plot, so what this basically is telling us is on the x-axis, the number of bits have been sent at microsampling of the relaxation oscillator, and on the y-axis, you have measured SNR, which basically backtracks to your number of bits, effective number of bits. For example, let's say bits, 30 to 40 dB is effectively 5 bits. So if you increase the number of bits to 4, you have effectively 50 dB, roughly talking about 6 bits. So without any hardware change, what we're saying is you change just the number of bits that you send, and because of the line spectral estimation in the analog compressive sensing domain, we can now try to reconstruct that or map that data points to an actual frequency, and that frequency then gets mapped back to the measurement that you are trying to measure through the sensor node. Okay, so there's no hardware change. The only thing that changes is a packet size. I hope that was clear. So with that, this was a simple demonstration that we did with the 4th channel. We had temperature sensors. For example, how many number of bits that you would like to send, and basically that sets the number of bits of resolution. Okay, and then with that we show that okay, we are actually able to reconstruct with varying degrees as well. So in conclusion, so what we are trying to say is, okay, you have a remote sensor node which you don't have physical access, but you would like to reconfigure it without doing any hardware change, but only a software change. So in this scenario, what we showed was you can actually do this with a compress sensing-based line structure estimation algorithm. Okay, and in future work, what we're trying to now do is, okay, what if there is a bit error when you transmit the actual data? How does that now backtrack to the effective number of bits that you get? So this is something that we are, which is under work, and probably will publish this again sometime. So I'd like to acknowledge my collaborators, Samir and Shuchin from Tufts and others. Yeah. With that, I conclude. Thanks.